Welcome to EDU World Space.
Problem 8.11. We have a poorly drawn rocket in outer space with a mass of 2,150 kilograms, and at time t equals 0, it starts firing an engine that produces a force that's proportional to time squared. And we're told that the value of this force at 1.25 seconds after it starts firing is 781.25 newtons. So we have several things we're supposed to find. The first of which is what is the numerical value with units of A. So if we know that, if we know T and F, then, we just solve this for A. It's going to be F of T divided by T squared. So this is 781.25 newtons divided by 1.25 seconds squared, and so this works out to be 500 newtons per second squared. And you can already tell what the units need to be just from this. This has to have units of newtons. This is going to have units of seconds squared, and so this needs to have units of newtons per second squared. So the units work out to what you would hope, and this is the number you get. Now, part B is a little bit more interesting. It asks us to find what is the impulse that this force produces. Does it exert on the rocket during the 1.5 second interval starting at 2 seconds after the t equals 0 when the engine starts firing? So we know that J is equal to the integral between 2 times of the force. And in this case, T1 is 2 seconds, and T2 will be 3.5 seconds. And so putting in AT squared here, A doesn't depend on time, so it comes out of the integral. Limits of integration don't change. T squared dt. And just from the integral rules for polynomials, we know that the integral of t squared is 1/3 t cubed. This has to be evaluated between R2 times, pardon me, and this ends up being 5,810 Newton seconds, which, as you'll recall, the impulse is also equal to the change in momentum. And so, Newton seconds has the same units. If you expand out what a Newton is, a kilogram meter per second squared, it ends up having units of kilogram meters per second. So this is the same as the units for momentum. Now in part C, what we want is to find what is the change in the rocket's speed. Because all of this is about the change in the momentum and everything. The actual initial speed of the rocket doesn't really matter. Before, there were no forces acting on it, and so it was in an inertial reference frame, and you could look at it from whatever inertial reference frame you like. and it wouldn't have changed anything. So we don't care what the speed was initially. It may have been 0, it could have been whatever. So we know, like I just said, that the impulse is equal to the change in momentum. And now the problem says to assume that the mass is constant of the rocket. So it doesn't change from this 2,150 kilograms, which is not how real rockets work, but it does make our lives a little bit easier here, because now m doesn't change, and so then this is going to become m delta v, and this is what we're looking for. So the change in the speed is going to be equal to the change in momentum, or the impulse, which we've already found, divided by the mass, which we're told. So you have the 5,810 Newton seconds here, 2,150 kilograms down here, and this works out to be 2.7 meters per second. And you can see that even though it's a fair amount of force that this is exerting over quite a while, because the mass of the rocket is so large, it doesn't speed up a whole lot in this 1.5 second interval, and that makes sense intuitively.